Hi guys, I am Priyanka Singh. Today we will discuss about statistical distribution in R. Basically, distribution means the probability of each value and we represent it in the form of graph. So this is all about distribution. Now let's basically get into it what exactly we are going to do. Basically, we are going to fit the distribution to data, which is a very common task in statistics. And we are using R package, that is fitdistrplus, which has several methods for fitting your parametric distribution. We're also going to see Descdist function, which provides classical descriptive techniques. So let's see how to implement all this code. So first of all, you have to implement or import your library, that is fitdistrplus. Then you have to import your another library, that is logspline. Because these two libraries are very important if you are going to fit your distribution as per the parametric equation. After that, we are going to use describe distribution function, that is DESCDIST. And then you have to put your column, that is a column must be continuous one. So here we are finding it for the sepal length. So this is basically a Cullen and Frey graph. It just shows you different distribution, and blue means your data points. So if we can see in the graph, our observation mostly lies in the uniform, logarithmic, normal distribution, and somewhat nearby to gamma as well as weibull. Here we get the skewness and kurtosis value also, because we got the statistic. Here we find out for petal length, because we have used comma 3. It is column number 3. So you can see it is mostly lying on the uniform. So what exactly fitdist function do? The plot of an object of class fitdist, it provides 4 classical goodness of fit plots. Basically, one is density plot, another one is CDF plot, then QQ plot, and then PP plot. So we'll now see all this plot. Because with the help of diagram, we are able to understand which distribution suits our column pretty well. Also, there are many techniques in which you can find the goodness of fit. We'll see all at once. So first of all, we'll use fit n, that is for normal distribution. So fitdist my data comma 1 and then norm. Norm is the name of normal distribution in this fitdist function. Now fit u means uniform. So we'll be fitting all those 5 distribution that we have seen in the Cullen and Frey graph. We have already seen that blue dot is mostly lying in that region, that is uniform, normal, logarithmic normal, weibull, and gamma function. So fit n for normal, fit u for uniform, fit l for logarithmic normal. And all this distribution we are doing it for sepal length. Another one is for fit g, that is for gamma. So just the same command, and you have to just correctly mention the name of distribution in the second parameter of fitdist function. So basically it is a gamma function, so I'll use that. Now the last one is fit w, that is for weibull. So fitdist my data comma 1, as I have mentioned it so many times, comma 1 denotes first column, that is sepal length, because it is continuous in nature, so we are using it. So here we have created all this distribution, and we have fit our data with this distribution. Now we are going to see the AIC value, different AIC value. For normally we got this AIC. For uniform, we'll get some another AIC. Basically, you don't get AIC for uniform with this method, but we'll see later how to find out the AIC and goodness of fit of different parametric distributions. Also mind, lesser the AIC value, more better is the fit of your distribution. So if you can see that L norm, that has logarithmic normal, has the least value of AIC, that is 367. So best fit of distribution for this column, that is sepal length, is logarithmic normal, that is lnorm. So this is what the inference you can draw. Now let's plot a diagram for all this distribution and let's see how well our distribution is best suited for our data. So we have initialized a console window for your visualization. Now we'll be creating all those four goodness of fit parameters, that is all those four graphs that are present in fitdist. I have already mentioned dense plot, so dense com, and I'm just showing you the syntax how to use this dense com. On similar basis, we will create for other three methods, like density plot diagram will create, QQ graph will create, PP will be there, and lastly CDF plot will also create. Because in the form of graphs and charts, we can easily distinguish which distribution is best suitable for our column, that is sepal length. So in this section of video, we're just going to see all this distribution in the form of charts and customized graph. After density plot, now we'll create for next plots that we have already mentioned. So here we are creating for QQ plot. Another one will be for CDF, and the last one will be for PP plot. So this is PP and the last one will be CDF plot. CDF means cumulative distribution function. So basically you have to look very carefully for the density along with that CDF. So you can see all this graph, and as far as I see, logarithmic normal, that is log norm, is best suited for this curve. You can easily see and distinguish all the curves. So the density plot is there, QQ plot is there, then PP plot is there, and lastly CDF is also there. So basically the goodness of fit of distribution we are calculating, it is done with the help of three main functions methods, that is cramer-von Mises, kolmogrov-smirnov, and lastly Anderson-Darling. So let's see how to use it. We will see all this goodness of fit with the help of function GOF star. Basically it will tell you all the AIC and BIC value which are related to each and every distribution, so you can clearly get an idea which distribution is best for your column name. And we'll be providing all the distribution name in this parameter, that is fit names. So we are using normal, we have used uniform, we have used log normal, that is logarithmic normal form, we have used gamma, and lastly weibull. So basically we'll get a summarized result of all this distribution. So yes, we clearly can get the idea of all these three tests that I have mentioned, and along with that AIC and BIC value is also there. So the least in all case is lnorm, if you can see. Even KS test value is least in lnorm, then AIC is least in lnorm, and BIC is also least in lnorm. So let's start with correlation. Basically, a correlation measures the relationship between two variables, that is how they are linked to each other. It is usually computed on two quantitative variables. So let's see how to do it. So now we are creating a data frame where we don't need qualitative variables. So in our case, in our data frame, the qualitative variables are species and size. So we will be dropping it off. So this is the syntax you have to follow for dropping those two columns. And let's see if we have successfully dropped our columns or not. So yes, we have successfully dropped those columns. So we are only left with sepal length, sepal width, petal length, and petal width. These are quantitative variables. And let's see the correlation between these two variables. These four variables, I mean that four quantitative variables. So now we are finding, we have got the correlation between sepal length and petal length. So that is positive 0.87. So that is, the variables are strongly related. Now we are finding out the correlation between sepal length because column 1 we are using and sepal width. So yes, negatively, as you can see, the more the width of your sepal, flower petal length, the less is the height. So we are justified with this correlation. So it is negatively related. Now we are finding out the correlation between petal length and petal width. It again will be positive value and quite huge value. So that means they are strongly related with each other. That is, higher the petal length, higher the petal width. So 0.9627. Any value more than 0.75 is considered to be strongly correlated. That is minus 0.75 to 0.75. Minus 0.75 means negatively related and positively. So here you can see the matrices, all the correlation value. You can clearly see the matrices. So here we are able to see that is sepal length related with sepal width with a value of minus 0.11, negatively related. Even sepal width, petal length is negatively related with value of minus 0.042. So this is how we calculate correlation between all those quantitative variable pair. Why we explicitly mention the method name? Because by default it takes Pearson, but we need to change the method, so we can do that as well. Just you have to mention the method name as Spearman explicitly. There are 3-4 methods like Pearson, Kendall, Spearman. You can use any of this. So if you want to see any data thing that we can draw from this inference, that is petal length and petal width are quite well connected and linked to each other. Now let's plot a graph, a very quick graph. So we have already seen how to use ggplot. Now we are passing those values on aesthetic with the help of ggplot to package. Just mention your x and y axis in the aesthetic parameter. So we are using sepal length and petal length. And let's see the data, how data points are, spread across those values. We're using point, geom underscore point. That means we're using scatter plot. We're coloring the dot. So blue is my favorite color, so I'm using it. So let's explore it. So you can see we clearly get some of the clusters also, like there are 2 clusters if you see, one is lower and one is upper. So you can see all those things by plotting the graph between these 2 variables. I'm just showing also without ggplot how can you plot. So simply you have to use plot function. So this is how you can visualize your correlation, relation, or the distribution of your point across those 2 variables. There is one interesting command, that is pairs. So you can see, with the help, so this is what I'm talking about. So you can clearly see the graph, like how sepal length, sepal width, and petal length are related to each other. So I can clearly see that sepal width and sepal length are negatively related, whereas sepal length and petal length are positively related. Now we are using another new library, that is korplot. This is done to see a very beautiful graph, a heat map kind of graph. So we'll see the exact value, and along with that some different color hues. Somewhere it is brighter, darker. So yeah, this is what I'm talking about. So sepal length, all those values are related in the form of chart, as I can infer from here. Now there is a function called core.test, which is again present in korplot library itself. We are finding the different p-values and all those Pearson coefficient value between sepal length and petal length. So you can get your correlation value, degree of freedom value, all those are present in core.test. Now it is a library called HMIS, so we have already installed it, now we are using it. So it has a function called rcore, and now we'll see a very beautiful summary of all the coefficient of correlation and all its value. So for summarized result, we can use this. So you can see what are the value of your p-value for each of the sepal length to sepal width combination. So for for knowing your p-value, you can use this. Now at last, there is a library called correlation. So you have to use this. You just have to explicitly mention your data frame name, because in our case, data frame name is data. Now just use include factors equals to true, method equals to auto, and then run this command so as to get your summarized result. So this is what I'm talking about. So degree of freedom is there, p-value is there, method is there. Now this is a user-defined function. Since we have already defined it, I'm just using it. So with the help of corplot2, you can also plot the graph with the help of user-defined function. So this is all about today's video. Thank you for watching. I hope you liked my video. So guys, please like, comment and share our video, and don't forget to subscribe. Thank you for watching.